Hello everyone. So in this video we are going to cover the combined gas laws. A lot of textbooks will try to teach this as three separate laws, which I think is kind of ridiculous. So I always teach this as one combined gas law, where the pressure of a gas times the volume of a gas divided by the temperature of a gas. If the pressure or the volume or the temperature are changed, this is the relationship between all those variables, okay? So everything over here is the initial pressure, temperature, volume. Everything over here is the final pressure, temperature, volume. And one thing to note here is that the temperatures must be in Kelvin. All right, and recall that to convert from Celsius to Kelvin, the Kelvin is just the Celsius value, and you add 273 to that. If you want to get picky, you really add 273.15. It's rare that we know the temperature out to decimal places, so generally speaking, we're just going to think of this as adding 273 and we're going to call it good, okay? But this is the equation you're going to use instead of using Charles' law or Boyle's law or whatever else you may have learned in the past. We're just going to use this one equation because, as you'll see, things that are constant will just get crossed out on both sides and turn into Boyle's and Charles and Gay-Lussac's law without you having to memorize those separate laws. On my exams, I'm going to give you this equation anyway, so you don't have to memorize it, but it does cut down on the confusion about which gas law to use because there's really only one. I will note that this is for samples of samples of gases that are heated or the volume is changed, and sometimes we say compressed if you're decreasing the volume, for example, or if you are changing the pressure in some way, okay? So related to those other two. So the point is, if you have a reaction equation that's creating gases, you can't use this equation. You need to use the ideal gas law, and that's covered in a separate video. But if you're talking about a single sample of gas that's being put in a container and you're heating it or you're cooling it or you're compressing it or you're pulling on it to increase the volume or you're doing something like that, then this equation, the combined gas law, is the one that you want to use. All right, so let's work an example. What's the final volume of a gas initially at 100 milliliters and 0 degrees Celsius, which is then heated to 100 Celsius at constant pressure? So this is a single gas that's being heated. And so let's just pull out what all the variables are. So we're told that it's initially at this. So that 100 milliliters is a measure of volume, right? So our V1 is 100 milliliters. And it's initially at 0 Celsius, so our T1 is 0, but remember that we're going to always add 273 to turn that into Kelvin. So that's at 273 Kelvin initially. And then we're going to heat it up to 100, so our T2 is 100 degrees Celsius, but again, we're going to add 273 to that. So 373 is our T2. We're asked what is the final volume, so V2 is our unknown. And then we're told that this takes place at constant pressure. Well, what does that mean? Well, that means when we pull out the combined gas law, the constant pressure, the pressure is the same here as it is here. So what that means is that those are going to cancel out, right? Because P1 and P2 are equal to each other, right? So it's just like having a 2 on the left and a 2 on the right. They just cancel out. And then that reduces then to this, which is pretty handy. Okay. Now, you can plug in the numbers from here into the equation and then solve. I like to solve and then plug in, but that's just me. You can do it how you want. I don't care either way. But I'm going to isolate V2 here by multiplying both sides by T2. Some people prefer to think of this as cross multiplication, and if that works for you, that's awesome. Do it that way. Totally fine. You're not hurting my feelings, okay? But I'm going to isolate V2 by multiplying both sides by T2. So I'm going to get that V2 is equal to T2 V1 over T1. And now all I have to do is plug in my numbers from over here. All right, so T2 is 373 Kelvin. And V1 is 100 milliliters. and T1 is 273 Kelvin, all right? And of course, I left my calculator at home. Why would I have my calculator with me? That would just make life much too easy. Fortunately, these aren't that much of a pain to do. So let's see here. So this is going to come out to be 136. Now, what's the units? Well, notice that Kelvin cancels, so you're left in milliliters. And we have 3 significant digits, so that's good. So actually, it's 137, my bad. For those of you calculating at home, you would have noticed that I had this off there. Okay, so that's 137. And does that make sense? Yeah, it does, because the temperature is going from 273 up to 373. So we expect the volume to go up, but not to double or anything like that. So 130 going from 100 to 137, that seems pretty reasonable. All right. Okay. I'm going to give you a practice problem, and I'd like you to pause the video and work this on your own, and then hit play when you're ready to see the answer. Okay, if you're stuck, I'll give you a hint. This phrase, fixed rigid walls, that means that you're at constant volume. Okay, because it just means the container is unable to expand in any way. So, all right, now I'm going to solve it. So I'm going to make a list of what I've got. So the pressure is going to increase from 1 to 2 atmospheres. So P1 is 1 atmosphere and P2 is 2 atmospheres. By the way, doing this where we pull the data out of the problem makes it so you don't have to reread the problem 16 times, right? You just have all the information down here, and now you can just, you don't need to reread the problem a 3rd time or 5th time, okay? So it's a really helpful technique, especially if you're just starting on a problem or if you're stuck. We're told the initial temperature, T1, is 25. I'm just going to add 273 to that and get 298 Kelvin. And we're asked to what temperature do we have to go? So T2 is our unknown. And volume is constant. So volume is going to cancel out. So now let's take out our combined gas law. And volume is constant. So we get P1 over T1 equals P2 over T2. All right. Now this is where folks get a little confused because you've got to solve for this T2 in the denominator here. I'm actually going to do this the way that you all tend to do it, which is students tend to plug in and then solve, which drives me a little crazy, but it's okay. You get the same answer. So when you set this up, it probably looked like this over, and I'm going to call it X. You can call it T2, doesn't matter. But the point is you've got to solve for that X. The only way to do this is you've got to get the X into a numerator. So the fastest way to do that is just to cross multiply, all right? So now you have 1.0 atmospheres times X equals 2.0 atmospheres times 298 Kelvin, all right? So I'm going to try to scoot this over a little bit so that it's not quite crammed in here. All right. So now we can divide both sides, we can divide both sides by 1 atmosphere. The units of atmospheres cancel. We're left in Kelvin, which is what we want, so this seems promising. So now we've got X equals 2 times 298, which is just below 600, 596 Kelvin. Okay, so that's our T2. Right? And again, you can't, back over here, you can't just move the P2 to the other side because you'd be left with 1 over T2, right? So it's really easiest if you think of this as cross multiplication to isolate a variable in the denominator like this, okay? So anyway, this is combined gas laws. The key thing is to pull the data out, make yourself kind of a little table, figure out what's constant, that's going to get canceled out. Isolate your variables, solve, algebra, easy peasy, okay? All right, hope this was helpful. Please let me know if you have any questions. Thanks a lot.